Okay, let's just begin. Okay, so today's lecture is about orthogonal subspaces, and the idea is as follows. Okay, so first let's demonstrate the idea with an example. Let's suppose we have a matrix A and we have the equation AX equals 0, right? So this is the homogeneous equation for which we're looking for the solution, and A is an m by n matrix. And the idea is we're looking for the values of x, which vector x, which when multiplied with this vector A get mapped onto 0, or as a linear transformation get mapped onto the 0 vector, or in terms of matrices get the matrix product is 0, so you get the 0 vector over here. And the idea is that if we look at this matrix product and write it down as summation xi ai, where ai's are the columns of A, so we have n columns. So you can view this as x1 times the first column A1 plus x2 times the second column A2 plus dot 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 up until the last vector xn, the last column an. And the result of this should be 0 0 dot 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 0. Okay, and so the idea is as follows. So if we consider any row, any ith row of this product, then the ith row would look like this. If I take the ith row, then the first one will be, the first term would be x1 ith row first column entry plus x2 times the ith row second column's entry plus dot 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 up until xn ith row and the nth column is equal to 0. And what does this tell me? This tells me that this x vector, if I can write this as x, then I can write this as perhaps xt times this thing. This is the ith row, right? So if I write it as r, the ith row of this matrix A, then this result is equals to 0. And notice that the notation that I'm using here is of dot products. So this is simply the dot product, the scalar product that we did in the last class. And the result is that the scalar product of x with the ith row of A is equals to 0, which means that x is orthogonal to the rows, because the I was arbitrary. You can take any row and you can have this result. So x is orthogonal to the rows of A, which means what? It means that now if it is orthogonal to any rows of A, it's also going to be, if we take a linear combination, let's suppose we take a linear combination y, or rather z, as some alpha r1 plus alpha r2, any linear combination of the rows of A, alpha r m, then if we multiply xt with z, what we will have is xt times this whole thing, which can be written as xt times alpha r1 plus xt times alpha r2 plus dot 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 xt times alpha rm. And since x is orthogonal to all of these r's, then the result is that you get 0 for all of these products. And essentially you get that not only is x orthogonal to all the rows, it is orthogonal to any linear combination of rows. And so notice that the linear combination, this z, is actually a member Z is a member of the row space of A, and X is a member of the null space of A. And the idea is that every vector X in the null space of A is orthogonal to every vector Z in the row space of A. So the row space of A and null space, we can say that the row space of A is orthogonal to the null space of A. Okay, and so that's the general idea. And so at this point we're ready to define what we mean by orthogonal subspaces. Orthogonal spaces. So the definition is that two subspaces of, notice that the row space of A belongs to Rn, and the null space of A also belongs to Rn. Actually, every vector belongs to Rn, and these are subspaces. If you recall, then these are subspaces. So for this is a subspace of Rn, and the null space is also a subspace of Rn. So if you have two subspaces X and Y are said to be orthogonal if xt y is 0 for every x belongs to X and for every y belongs to capital Y. So if you take any vector from this subspace, and you take any vector from this subspace, and if the result is, if the scalar product is 0 for every possible combination of these vectors, then this is known to be as orthogonal. The subspaces are called orthogonal to each other. So let's do an example here. An example is the following. So let X be the subspace, be the span of E1, and let Y be the span of E2. Then if we take X, if X is in the span of E1, that means X is basically a alpha times E1, which is basically a vector that looks like that has only something in the first component. So let's suppose we have x1 and 0 here and 0 here. And if Y is spanned by E2, then it's basically alpha E2. So it has only something in the second component and nothing else. And if I take the dot product of these two vectors, of course, it's going to be x1 times 0 plus 0 times y2 plus 0, and the result is 0. So these two subspaces X and Y, then X and Y are orthogonal to each other. This symbol stands for orthogonality. So this means orthogonal. Okay. All right. Let's do another example. Notice something, that there is a difference. If you think about the plane, if you think about the plane, this is the this is the YZ plane, and this is the XY plane. These planes, even though they look perpendicular to each other, in some ways they are in a certain intuitive notion they are perpendicular, but these are not orthogonal subspaces. The reason is, notice that they have a common vector that they share. So if I take this line is common between both of them, and if I take any vector on this line, let's suppose this green vector, or let's make it more visible, let's take this orange vector, and the idea is, if you consider this orange vector, let's call this v, then v belongs to yz, and v also yz plane, and v also belongs to xy, and v is clearly not going to be, so if it's any vector, it's let's suppose 0 1 0, so this vector will be in the y-axis, which is common to both of these planes. If I take the dot product of v with itself, then this is equals to 1 and not equals to 0, which means it doesn't work for every possible vector in this. So I took the same vector which was common to both of them, and therefore that it doesn't work. So these xy plane and yz and xy planes are not orthogonal to each other. They're not orthogonal subspaces in that sense. But of course, physically they do make an angle of 90 degrees. The way you get an orthogonal subspace is as follows. Consider you have the xy plane again, and you consider a direction in the opposite. So let's suppose this is the xy plane. So vectors in this space, so let's call this is the red space and this is the orange space. Vectors in the orange space, let's call this x. So vectors that belong to the orange space have form some x1 and some x2 and 0. But if you take a vector in this space, then my contention is that they should only be in this direction. So they should be spanned by E3. That is, any vector in the red space looks like this. It's 0, 0, both these components are 0, and the last one is 3. And now if you notice, if you take the dot product of any two such vectors, then the dot product of x dot y is going to be equals to x1 dot 0 plus x2 dot 0 plus 0 dot y3. And now you can see that for any two vectors in these two subspaces, you have the result. Over here we did not have this because vectors in this space can be written as x1, x2, 0, and vectors in this space can be written as there is no x component, but there is a y component and there is a z component. And so when you take the dot product of this and the dot product of this may not necessarily be 0, it's going to be equal to x2 dot y2. And that's not guaranteed to be 0. It may be 0 in some particular cases, but not 0 in all possible cases. Okay. All right. And so the next thing is, we define a concept of, define orthogonal complements. And the idea is as follows: let Y be a subspace of Rn, then the set of all vectors in Rn that are orthogonal to every vector in Y will be denoted by this symbol Y complement, and we define it as Y complement. It contains every vector x in Rn such that x ty is equals to 0 for every y in the subspace that we're looking for. And this thing, this y complement, this is called the orthogonal complement of y. So what do? You take this vector space and you take every possible vector, you collect all those vectors whose dot product with vectors in this space is equals to 0, and you make a collection out of those vectors and you call that the orthogonal complement of y. Okay, and so for example, let's suppose you have, as an example, consider first what we were looking at. We have x is equals to the span of E1 and y was the span of E2. Notice that these are orthogonal to each other. X is orthogonal to y, but y is not the orthogonal complement of x, because the vectors that are perpendicular to vectors in x will actually be of the following form. So the orthogonal complement of x will not only be the span of just E2, but it will be the span of E2 and E3. We're looking for, note that we're working in R3 right now. And similarly, the orthogonal complement of y will be the span of E1 and E3. So let me just show you how. So if x was the span of E1, then x, if there is a vector x in this capital X, it can be written as x1, 0, 0. And if there is a vector in the orthogonal complement, it can be written as 0, x2 and x3. And notice, if you take any vector of this form, and let's call this x prime, that belongs to the x complement. If you take any vector of this form and you multiply it with any vector of this form, the result is definitely going to be 0. And so you can check for y and y complement as well. Okay. And so a couple of remarks. Firstly, so remark number 1, the first thing is that if x and y are orthogonal subspaces of Rn, then, so if you have two subspaces which are orthogonal to each other, then there will be nothing in their intersection. There is no common vector between them. And secondly, because if there were a vector that was common in them, then their dot product for every possibility, just as we saw in this example, that if they have anything in common, if you take the dot product of that with itself, you will not get the 0 vector. So any non-zero vector cannot be in their intersection. And the second comment is that if y is a subspace of Rn, then y, the orthogonal complement of y, is also a subspace of Rn. And so the first one is quite easy to see. The second one we can check as follows. The proof, let's try to do the proof for the second one, proof for 2. And the proof is as follows. Consider the following. If you have any vector in this space, then it's a subspace. To prove it's a subspace, you have to show two things. You have to show that alpha times x also belongs to this space, that is, it's closed under scalar multiplication, and it is closed under addition, so x1 plus x2. So if x1 and x2 belong to this space, then x1 and x2 should also belong in this complement, and that's easy to see. So we do the proof. It's easy to see because if x belongs to this space, then that means x, if y belongs to this complement, then x transpose y is going to be 0 for all y. And now if I consider alpha x and if I check, so this tells me this is y, which I can rewrite as alpha x transpose y, but I know that alpha x transpose y is simply 0, which means that alpha x is also in the orthogonal complement, because this vector was orthogonal to every possible vector y in this space. And secondly, if x1 and x2 belong to the orthogonal complement, then we have that x1 plus x2, if I take the scalar product, then what we get is x1 transpose y plus x2 transpose y. Because it's a linear operation, you can do that. And so this is 0 and this is 0, so this is also 0, which implies that x1 plus x2 also belongs in the orthogonal complement of y. Okay. All right. So now we have the idea of fundamental subspaces, and this is related to something, perhaps if you've seen the MIT video that I've posted by Gilbert Strang, he talks about these subspaces as well. Okay, and so here is the theorem. Actually, let's just first talk about what we are going to talk about first. So consider the following. We call RA is basically the range of A. Consider you're talking about, let's suppose you're talking about an m by n matrix, right? So an m by n matrix can be seen as a linear transformation from Rn to Rm. And the idea is that the range of this transformation is basically every vector B. So B belongs to Rm. The range of this will be every vector, every possible vector, such that B is A times X. Okay? And so for some X belongs to Rn. The idea is that you are looking at the same thing from two different angles. The first thing is you're considering the matrix vector product of an m by n matrix with an n by 1 vector, and the result that you get is an m by 1 vector. And so what we are saying is that this vector contains this space, the range of A contains all these possible products which you get when you multiply A with X, right? And the other thing, the linear transformation view, is that you have Rn and you're mapping Rm. So you're mapping it into Rm, and all of the range, the possible results, the column space basically is called the Ra. So you can consider it in two different ways. You can consider it to be the column space, because of course this can be written as summation xi ai. So matrix vector products are just the column space. So Ra is the range of the linear transformation by A, or you can think about this as the column space of A. Okay. And now consider something different. So what if I transpose this matrix? If A was an m by n matrix, then At is an n by m matrix. And so I can define, again similarly, the range of At. The range of At is of course the column space of At, but we know that this is essentially the same as the row space of the original matrix. So RAT properly defined is simply all the vectors B such that B is equals to A transpose times X for some X in Rm now, not Rn, in Rm. Okay, and so this is the row space. So the column space of the transpose is the same as the row space of A. And something that we've already seen, something that we saw at the start of the lecture, as an example rather, was that I established that the row space of A is orthogonal to the null space of A, which basically means that, so this row space, which is the same as the column space of At, what I can say is that if this range of At is orthogonal to the null space of A. Okay, all right. And we have actually a nice little theorem that tells us something further than that not only that these two spaces are orthogonal to each other, they are also, so for if A is an m by n matrix, then the null space of A is not only orthogonal to it, but it's actually equals to the orthogonal complement of this row space. And something further, we can switch these and we can say that the null space of A transpose, if you reverse the argument and look at it from another perspective, if you consider column space, then this, what you're essentially saying, that the null space of the transpose is going to be equal to the orthogonal complement of the column space of A. So notice something, this is the column space of A, and we're saying that the column space of A is orthogonal to the null space of the transpose. And over here we are saying that the orthogonal complement of the column space of A, so this is actually two things. So this is not only the column space of A transpose, but it's also the row space of A. And similarly, this, if you call this the column space of A transpose of A, then it's also the row space of A transpose. Okay, and so the null space of A will be orthogonal, will be the orthogonal complement of the row space of At. And so let's check this, let's prove this first, and once we prove this, we'll be able to use it. Okay, and so here's the proof. All right, so let's start to prove this proof. The first thing that we have in the proof is, notice that the null space we've already shown. We've shown that the null space of A is orthogonal. This is something that we did at the start of the lecture, that the null space is orthogonal. So if it's orthogonal, then it's going to be a subspace of the orthogonal complement of this, because notice that the orthogonal complement RAT is complement contains is actually equals to, it contains all the vectors x such that x t y is equals to 0 for all y's in a, for all y's in this space, in R A transpose. So whatever vector you have, the collection of these orthogonal complement will contain all possible orthogonal vectors. But if the null space is orthogonal to it, then we know that all the vectors in this are of this form. So all of them will automatically be in this space. So it's going to be a subspace of the complement. And the question is, are there any other vectors in this complement, orthogonal complement, other than the null space, other than the vectors that were found in the null space? And the answer is no, there's no other vectors, only these vectors are included. And the way we see that is as follows. Consider let X belong to the row space, the orthogonal complement of this. And so then X, this means that X is orthogonal to every vector in the column space of AT. And what does that tell us? It tells us that AX, if I write it as, okay, let's rewrite this. Let's write this as if A equals to A1, A2, AN. And since X is in the column space of AT, that means, alright, so if A is in the orthogonal complement of this, then that means that A must be, so AT is a transformation from Rm to Rn, right? And so this tells us that X will be a vector in Rn. And so if it's orthogonal to every column of AT, then it's going to be orthogonal to every row of A. And so if I write it like this, if I take the columns of AT, which were A1 and so on, and if I write them out for A, which are going to be the rows A1 A2, then A times X, you can check that this is going to be equals to 0, because when you do row times column, then this row will be multiplied with this column, and so you will get that A1t x is equals to 0. Therefore you get Ax is equals to 0, which essentially means that X is in the null space of A. So this is how we view it. Again, let me repeat. So we were viewing this as columns, and what we were saying that it was orthogonal to every vector in the column space of AT. And column space of AT is nothing but any vector written as a linear combination of, let's suppose, alpha A1 plus alpha 1, alpha 2, A2, and so on. And if it's orthogonal to every column vector, then it's orthogonal to this. And so if X is orthogonal to every column here, then it's going to be orthogonal to every row here. And so this matrix vector product will also give me a 0. And so that tells me that if I take any, what does that tell me? It tells me that if I take any vector in the orthogonal complement, I will get a vector in the null space. So we've shown that the orthogonal complement of the column space of A transpose is a subset of this. Therefore we have this relationship both ways. Therefore it means that the null space of A is the same as the row, as the orthogonal complement of the column space of the A transpose. And so since we did not use any dimensions, then I can just say that if B is equals to A transpose, so if I take the null space of P, it's going to be equals to the orthogonal complement of B transpose, then I can write this as the null space of A transpose is equals to the orthogonal complement of the column space of A transpose transpose is simply A. So it works both ways. Oops. And so it works both ways. This is the first relationship and this is the second relationship. All right. Okay. So let's consider an example. Consider A to be the matrix 1, 0, 2, 0, and the idea is if X is in R2, then AX, any vector B which is equals to A times X, looks like this: 1, 0, 2, 0, X1, X2, which is actually equals to 1 times X1 and 2 times X2, which can be written as X1, 1, 2. And so what do we have here? This is the column space of A. So this is essentially R of A contains all vectors of the form. So R of A contains all vectors of the form X such that they're equals to sum alpha times 1, 2 transpose. So you multiply any constant with this, and this any vector will be of this form 1, 2, depending on what X1 is in the X matrix, original matrix. So any column vector will be of this form. Okay, and so the question is, what about the null space? And we have to check, what we need to check, that the null space, by the theorem above, we know that the orthogonal complement of this will be the null space of A transpose. So if I consider A transpose, let's perhaps do this whole thing. A transpose is simply 1, 2, 0, 0. And if I want to compute the null space, then I just multiply ATX, and I find that I have 1, 2, 0, 0. I want X1, X2, and this should be equals to 0, 0. And so what do I have in this case? I have the following. I have the equations x1 plus x2 is equals to 0, and so x1 plus 2x2, so taking the first row and the first column, x1 plus 2x2 equals to 0, so x1 is equals to minus 2x2, and so if I write any vector x1, x2, this can be written as, actually it's simply minus 2x2 and x2, because x1 is simply minus 2 times x2. So it can essentially be written as sum beta. So the null space of A transpose is essentially equal to all vectors x such that x is equals to, it should have been x is equals to some constant times minus 2 and 1. So all such vectors will be in the null space of A transpose. And now notice what happens. If I take any vector of the form alpha 1, 2 transpose, so if I take any vector of the form alpha 1, 2 transpose, this should also be transpose, and if the other vector is beta minus 2, 1 transpose, if I try to compute their scalar product, the scalar product will be as follows. So the scalar product will be alpha so what I should essentially have, so actually let's remove alpha. We can separate alphas and betas because they are just constants, you can take them out. And so what you will have if you take dot product of these two, this with this is 1 times minus 2 plus, actually let's just include alphas and betas so that there's no confusion, alpha and beta. So if I take the product, then that will be equals to 1 times alpha x1 times minus 2 times beta plus 2 times alpha multiplied by 1 times beta, and what you have here is minus 2 alpha beta plus 2 alpha beta equals to 0. So you can see clearly that any vector in the column space of A is going to be orthogonal. Okay, so next up we have a nice little theorem which says the following. If S is a subspace of Rn, then the dimensions of S plus the dimensions of the orthogonal complement of S is equals to n, which is basically the dimension of the space that you're working in. So if you have a subspace and if you take the orthogonal complement of that subspace and if you add their dimensions together, you should get n. And this might look a little familiar to you if you remember the rank nullity theorem that we did in the previous lecture, which is closely related to this. We'll actually use the rank nullity theorem to prove this statement. And so the idea is as follows, and furthermore, if you have a basis, if x1 to xn is a basis, xr is a basis for S, and if xr plus 1 up until xn is a basis for S complement, S the orthogonal complement of S. The idea is I have taken a total of n vectors because I know that both of their dimensions will sum up to n. So if this one has r basis vectors, then this one will have n minus r basis vectors, and so the total is this. And the idea is that if this is true and this is true, then x1 dot 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 xr plus 1 dot 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 xn, if you combine all of these basis vectors together, then this is a basis for the n-dimensional real space, which is pretty neat, right? So if you have a basis for this space and if you have a basis for its orthogonal complement, you have a basis for your whole space. And so let's try to prove this. So the proof is as follows. The first thing to notice is if S, the subspace that you're talking about, if it's the trivial subspace, then the trivial subspace will have the orthogonal complement of the trivial subspace will be the entire n space. And why is that? That's because if you take any vector in this space, which is of course 0 vector, and if you take any vector in, let's suppose, Rn, then if you multiply both of these, if you multiply any real number, any n-dimensional n tuple, then what you get is y xty is definitely going to be equal to 0. And so the orthogonal complement contains all possible vectors that will give a dot product of 0 with this x. But if you want a vector that gives the 0 results with the 0 vector, then you can take any vector from Rn. And so in this case, of course, the dimensions of this space, and so for this one it's trivial because the dimensions of S plus the dimensions of S complement are simply 0, because you have the trivial subspace and you have the entire n space, and this is of course equals to 1. So it checks out in the first case. But assume, let's suppose we have the case when it's not the trivial subspace. So let's suppose S is not the trivial subspace. Then let's get a basis x1 to xr, a basis for my vector space, and we define X as an R by N matrix such that the ith row is xi transpose. So what we're essentially doing is we're building a matrix. We have built a matrix whose rows are as follows. The first row is x1 transpose, the second row is x2 transpose, and the last row is xr transpose. And so there are r rows, and because each vector belongs to Rn, they're going to be n columns because there are going to be n entries in each vector. Okay, and so we know the following. By construction, we know, by construction, when I say by construction, it's because the way we've built this matrix, we are guaranteed something. We are guaranteed that if I consider the row space is going to be the same as just some linear combination of the rows, and the linear combination of rows gives me S. So the row space will have, and so the idea is that the matrix, the row space will have dimensions of the row space is going to be R, because that's essentially the dimensions of S, right? And if you notice, then the row space, then the range of X transpose. So if I take the X transpose, then that's just going to make it, so this was matrix X. If I transpose this matrix, then all the rows will become columns, and then the column space will become, the range of xt will become just S, because you've just converted the row space into the column space, and that's just essentially S. And now notice we have the rank nullity theorem. The rank nullity theorem tells us the following. The rank nullity theorem tells us that the dimension, that the rank plus nullity is equals to n, and rank is nothing but the dimensions of the row space. So the dimensions of the row space are simply R, and nullity is simply the null space of this matrix X. So the nullity is going to be, the null space of X is going to be n minus R. But here's the thing. Since X transpose is S, then I know that the orthogonal complement of xt is the same, orthogonal complement of the column space of xt is simply S, but we've shown it in the previous theorem that this is nothing but the null space. So if you want the orthogonal complement of the column space of the transpose, then you just look at the null space. And so this is nothing but, both of these are just the orthogonal complement of this subspace S. And so this is essentially, so this, I've written this incorrectly. This should be, the nullity means the dimensions. and so what we have is this was equals to r, and so the dimensions of nx, which means basically the dimensions of S complement, the dimensions of S complement is equals to n minus r, and there we're done, because we just said that the dimensions of S are r and the dimensions of S complement, the orthogonal complement of S is n minus r. Therefore, if you add these together, r plus n minus r is going to give you r, and this works out when you don't have the trivial subspace. Okay, and so let's just do the following. Let's complete the proof by showing that indeed what we have to show is that x1 to xr and xr plus 1 dot 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 xn is a basis for Rn, and let's try to do that. How do we do that? Well, consider a vector. If we take any linear combination, let's suppose I take linear combination, what I'm going to attempt is to show that all of these x1s, this collection x1 up until xn, this collection is linearly independent. And we know that if we have n linearly independent vectors in Rn, then it forms a basis. So all I need to do is show that they're linearly independent. And the way to show that they're linearly independent is to show that if I take a linear combination c1 x1 plus c2 x2 plus dot 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 cn xn, then this is equals to 0. We have to show that this summation is only going to be 0 if all ci's are equals to 0. That's something that we have to show. And of course we can show that. The way we show that is as follows. So if I consider the first r of these, if I take the first r of these up until r and the next n minus r, call y c1 x1 plus c2 x2 plus dot 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 c3 xr. I know that if I take just the first r vectors, since they formed a basis, then they are definitely, their linear combination is going to be 0 if and only if, actually let's just write this as this, z equals to cr plus 1, oops, this should be cr, so cr plus 1 xr plus 1 plus dot 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 cn xn. And so what we've done is we've written y plus c is equals to 0. So I've just written the first r of them, combined them into y, and the next ones as z, and so we have y plus z equals 0. And notice that what we will get is y equals minus c. Now this is something strange, because y is just a combination of the first r vectors, which means it should be in S, and z is a combination of all of the rest of them, which means it should be in the orthogonal complement. Therefore, what it tells me is that if both of them are equal, then we have a vector y which is essentially in both of these elements. So y and z are in both, because a scalar multiplication is going to be in the same space as well. So are in both S and S complement, the orthogonal complement of S, which means that y and z belong to the intersection of these complements. But we know that that's not possible. It's not possible because the intersection of two spaces which are orthogonal to each other, made a couple of remarks, here it is. So if these are two orthogonal subspaces, then there's going to be nothing in there. The only vector common to them has to be the 0 vector. And so this tells us that y is going to be 0 and z is going to be 0. So first it tells me that y has to be 0 and z has to be 0. But if y has to be 0, which means that c1 x1 plus c2 x2 plus dot 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 cr xr has to be 0. But since I have a guarantee for at least these are vectors that they're linearly independent, c1 up until cr are going to be 0, because they can only be 0 since these are linearly independent vectors which form a basis, because they have to be linearly independent because they form a basis. So we have at least these ci's are guaranteed to be 0. And similarly, if we take cr plus 1, xr, which was basically z, and you add up all of them, c2 cr plus 2 xr plus 2, what you have at dot 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 plus cn xn, since these vectors also formed a basis for S complement, then I am assured that cr plus 1 dot 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 cn's are also equals to 0. And so therefore I have shown that c1 to cr to cr plus 1, all of these cn's are equals to 0, which completes the proof that all of these vectors are linearly independent. Which means if they are linearly independent, then x1 to xn are n linearly independent vectors in Rn. Therefore it is a basis for Rn, and that completes the proof. There's few other things that are left in this section, and I think I'll leave this up until here at this point, and we'll do the rest of them in the next section.